Hello everyone, so today we're going to go over section 8.2 part A, sum, difference, and double angle identities. So we'll begin by looking at this expression here. Sine alpha plus beta is equal to sine alpha plus sine beta, and it is not a trigonometric identity, and we'll show that numerically. So we're going to let alpha be equal to 30 degrees, and beta will be 60 degrees. So as we know from before, sine 30 degrees is equal to 1/2, and sine 60 degrees is equal to √3/2. Okay, so if this expression were correct, then we'll have something like sine 30 degrees plus 60 degrees is equal to sine 30 degrees plus sine 60 degrees. So the left-hand side, we can simplify by adding the angles together, and that's sine 90 degrees. The right-hand side, we can evaluate sine 30 degrees to be 1/2, and sine 60 degrees to be the square root of 3/2. However, we know that sine 90 degrees is equal to 1, so we have 1 is equal to 1/2 plus √3/2, which of course is not true. So therefore, sine alpha plus beta equals to sine alpha plus sine beta is not an identity. And to show that an expression is not an identity, we just have to show it for one value. In this case, we let alpha be 30 and beta be 60 degrees, and that is sufficient to show that it is not an identity. So the true sum and difference identity for sine, cosine, and also tangent are in this box here. So on the left-hand side, we have the sine, sum, and difference identities. On the right-hand side, we have the cosine, sum, and difference identities. And then at the bottom row, these are for tangent. Okay. So we can now verify the actual identity that works using, instead of 30 and 60 degrees, we can use pi/6 and pi/3, which of course will function in much the same way. So this time around, on the left-hand side, we have sine, and we can let alpha be pi/6. So this is pi/6 plus pi/3, which is beta. And it's going to be equal to sine pi/6 cosine pi/3 plus cosine pi/6 and then sine pi/3. So the left-hand side, we can add these two together, and we actually get on the left-hand side sine of 3pi/6, which of course is equal to just pi/2. And we know that sine pi/2 is just 1. So on the left-hand side, we'll simply have 1. On the right-hand side, sine pi/6 is 1/2. Cosine pi/3 is also 1/2. We can use the special triangle on the right to figure this out. So for example, sine pi/6, we are looking at the opposite side, that's 1/2. For cosine pi/3, adjacent side is also 1/2, so that's how we can use this special triangle. And likewise, for cosine pi/6, we'll have √3/2 right here. And then for sine pi/3, again, the opposite side, √3/2. So this would be, of course, then the square root of 3/2 multiplied by the square root of 3/2. So 1/2 times 1/2 is a quarter. And root 3 over 2 times root 3 over 2 is 3/4. And if we add those together, we do get 1 equals 1. And so at least for the values of pi over 6 and pi over 3, the sum identity works. And working with the identities allows us to find exact trigonometric values for angles that were not possible before. Okay, consider first sine pi over 12. So pi over 12 is not in any of the special triangle, in neither of the special triangle, really, there are only two. But suppose we rewrite pi over 12 like this. So we can rewrite pi over 12 as pi over 4 minus pi over 6. Right? Since we can, if we rewrite these two here with a common denominator, we'll have 3 pi over 12 minus 2 pi over 12, which of course is pi over 12. So that means instead of writing sine pi over 12, we can write it as a difference of pi over 4 and pi over 6. So like this. And from there, we can use the difference identity for sine to further split up the expression. So we have sine pi over 4, cosine pi over 6, and then minus cosine pi over 4, and finally sine pi over 6. So using once again our special triangle values now, sine pi over 4 is 1 over root 2. And then cosine pi over 6 is root 3 over 2. And then cosine pi over 4 is also 1 over root 2. And pi over 6 is 1/2. So that means our first term here is going to be root 2 over 2 root 2. And the second term will be 1 over 2 root 2. And we actually have common denominators already, so we can subtract the numerators. So we have root 3 minus 1 all over 2 root 2. Oops, sorry about that. Now, if we were to rationalize the denominator by multiplying each term by root 2, then we can rewrite this as the square root of 6 minus the square root of 2 all over 4. And that's what we get for rationalizing when we're rationalizing the denominator. On the right-hand side, we can do something very similar. So 105 degrees can be rewritten as 60 degrees plus 45 degrees. So very similar to the left-hand side. Now, of course, we're going to use the tangent sum identity instead. So we have tangent 45 degrees plus 60 degrees. And then that would be split up into tangent 45 degrees plus tangent 60 degrees all over 1 minus, and then tangent 45 degrees times tangent 60 degrees. So of course the good news here is that tangent of 45 degrees is just 1. So we have in the numerator 1 plus, and then tangent of 60 degrees using our special triangle from above is going to be the square root of 3. And so the numerator will be then 1 minus 1 times root 3, so just root 3. And now, of course, this could also be, the denominator can also be rationalized here, but generally, if we leave it as 1 plus root 3 over 1 minus root 3, that is sufficient as an answer. So for the next example, it's a little bit different. So it's kind of like the reverse. The expressions are already expanded, and we're trying to combine them into something simpler. So it says write each expression as a single trigonometric expression. It should say expression, not function, and then evaluate the exact value. So it's going to correct that here. This really should be an expression. Sorry about that. Okay, so we can let the first 27 degrees be alpha, and then the 57 degrees be beta. And notice that this is actually the difference identity for sine. So we can rewrite this as just sine 27 degrees minus 57 degrees. Okay, the order matters here because it is a difference. So we'll get sine negative 30 degrees. From there, we can use the reference angle of 30 degrees. And of course, then we know sine 30 degrees is equal to 1/2. But sine negative 30 degrees is in quadrant 4, and sine ratios have to be negative there, so we're going to get a value of negative 1/2. Alternatively, of course, we can just use a calculator for this one, and it will also give us negative 1/2. On the right-hand side, something very similar. Here we have cosine 5 pi over 9, cosine pi over 9 minus sine pi over 9, sine 5 pi over 9. So again, same kind of thinking here. We'll let 5 pi over 9 be alpha, and then pi over 9 be beta. And this is actually the sum identity for cosine. So we can rewrite this as cosine of 5 pi over 9 plus pi over 9. So of course, this can be rewritten as 6 pi over 9, which could be simplified to just 2 pi over 3. So cosine 2 pi over 3 is what we're looking for. So again, using the reference angle, this time the reference angle will be pi over 3. And we know that cosine pi over 3 is equal to 1/2. But 2 pi over 3 is in quadrant 2, and cosine ratios are negative there, so this is also negative 1/2. So if we're giving something that's already expanded using sum and difference identity, we can rewrite it as a single trigonometric expression and then evaluate it from there. So next question. So it says here the point 3, 4 is on the terminal arm of angle x in standard position. Then what is the value of sine pi plus x? So the first thing we're going to do here is draw the point. So let's look at it. Here is 3, 4. Let's draw it this way. So here's the point. So we have 3, 4. And of course, using the Pythagorean theorem, 3 squared plus 4 squared is 25. So we know that this hypotenuse is 5. And the angle right here is x. Okay, so we know that, let's use a different color. So here we have sine pi plus x. We can expand this using the sum identity. So this is sine pi cosine x plus sine x cosine pi. Now sine pi is equal to 0. And then cosine x, we don't know the value of just yet. And we have in the second part of the expression sine x, and then cosine pi is negative 1. So ultimately, this actually simplifies to just negative sine x. And as we know, sine x is equal to opposite over the hypotenuse, so we have 4 over 5. So this will just be negative 4 over 5. And that's it. So next question. Example 7. So it says if sine alpha is equal to 3 over 5 and cosine beta is equal to 24 over 25 and both alpha and beta are acute, so they're in quadrant 1, determine the exact value. So before we expand this, in all likelihood, we're going to need the values of cosine alpha and sine beta in order to do this question. So I'm just going to go ahead and find them before proceeding here. So that means that the opposite side is 3, and then we have 5. So we have this triangle here. The opposite side is 3. The hypotenuse 5. So again, we have the 3, 4, 5 triangle in quadrant 1, which means that cosine alpha should have been 4 over 5. And then in the second triangle, we can do something very similar. So here we have the x value is 24. The r value is 25. So let's go ahead and draw those in. So this is 24. This is 25. And this is... so we have to use the Pythagorean theorem to figure out what the y value is in this case. 25 squared is 625 minus 24 squared, which is 576. The difference is 49. So the square root of that is 7. So this is the 24, 7, 25 triangle. So that means sine beta must have been 7 over 25. And we know that these ratios are both positive because both alpha and beta are in quadrant 1 because they are acute. So we can proceed from here. Okay, so the first part, it says sine alpha plus beta. That is equal to, of course, sine alpha cosine beta plus sine beta and then cosine alpha. And from there, we can substitute the values that we found. So we know that sine alpha is 3 over 5. Cosine beta is 24 over 25. And then from there, sine beta is 7 over 25, as we found earlier. And that cosine alpha is 4 over 5. So the two parts, the first part, 3 times 24, is 72. This is going to be over 125. And the second part, 7 times 4, is 28. And that's also over 125. So when we add the numerators together, that's 100 over 125, which actually simplifies to just 4 over 5. Okay, and then the second part, we're looking at cosine alpha plus beta. So that means we have cosine alpha cosine beta minus sine alpha sine beta. Again, using the identity. So here we're going to have cosine alpha, which is 4 over 5. And then cosine beta, which is 24 over 25. And then minus sine alpha, which is 3 over 5. And then sine beta, which is 7 over 25. And very similar to the previous question, we now have 4 times 24, which is 96 over 125. The denominators will be the same in this case as the previous example. And then 3 times 7 is 21, again over 125. The difference is 75. So this would be 75 over 125, which of course simplifies to just 3 over 5. And that's it. So that's the sum and difference identity for sine, cosine, and also tangent, although we only did one example for the tangent sum and difference identity. A lot of times, the questions will be about the sine and cosine sum and difference identities. They're more likely to appear than the tangent one in general. But that's it for today. So once again, thank you for listening.